Okay. Started. So what we want to do today is we want to talk about the standard normal distribution. This is section 7. I want to talk a little bit about normal distributions. I want to go back and just kind of review a few things. We're going to be working with the normal distributions throughout the entire semester. So this distribution is so important that we definitely want to spend a little time looking at it in more depth, okay? So just to review quickly, key things about a normal distribution: has a very distinctive bell shape, and we said that the probabilities follow the empirical law exactly. So that was really important. You can think of that as a defining characteristic, actually, okay? Now, the empirical rule, we're going to be using this a lot, okay? So the thing to remember is that when we have mound-shaped distributions, the data that we're looking at can be either from a sample or from a population, okay? And so here, we're going to have data from a sample, right? This isn't a curve, this is a histogram. The key thing to remember is that the empirical rule is not obeyed exactly. So this is approximate for a mound-shaped distribution. When you go to a normal distribution, whenever we're talking about normal distributions, we're always talking about populations now. We're not talking about samples anymore. And you can tell that because if you look at this, you can see this curve. We're talking about a curve. We're talking about a population. And the empirical rules obeyed exactly. So this is a really important part of the empirical rule for normal distributions. So we talked about parameters also. So for the normal distribution, the parameters are going to describe what the shape of that plot looks like, okay? And so we said that for a normal distribution, when you went into StatCrunch, there were two things you had to tell it. You had to tell it the mean. And so this is the parameter. Mu is the parameter that's describing the center of that plot. And you had to tell it the standard deviation. That's the parameter that's describing the width, okay? This notion of parameters is going to be something we talk about a lot. Now, this is something new that we haven't covered so far. The book uses this notation, and I'm really glad it does, because this is really useful and it's a really nice shorthand. So sometimes when we want to express a normal distribution, we'll use this sort of notation. And remember at the very beginning of class, I said one of the hard things about mathematics sometimes is we take really simple things and we make them really look, really complicated. Well, this is a little bit of an example, but I think it's kind of worth it. So what this means, here's how we read these, okay? We read this as the random variable x. So whenever you see a capital X, that's always just some random variable. And that little tilde is distributed like. That's how we pronounce that. And that n is a normal random variable, not surprisingly, right? And finally, we have to give the mean and the standard deviation. So we're familiar with these things. So let's just kind of run through an example and see how to use this, okay? So suppose we go back to that SOB example, right, where we said that it kind of looked like a normal random variable, had a mean of 29.5 thousand and a standard deviation of 5. So if I wanted to write that in this shorthand notation, this is how I would write it. I say that this is a random variable that has a normal distribution, the mean of 29.5, the standard deviation is 3.5. So just as a kind of quiz to test how well we know this, suppose, for example, I wanted to use this notation to write this normal random variable. How would I do that? I want to write using this notation, this random variable. How would I do that? Take a shot.
So the x, like, we're doing minus signs.
Tilde?
Yep. And parentheses and comma.
Excellent. So notice that when we give a normal distribution and we give the mean and the standard deviation, we actually enter the values. So this would be read as x has a normal distribution with a mean of 10 and a standard deviation of 2. I've kind of parsed out the words so that you can understand what these things stand for, but usually we just say x has a normal distribution. That's how we say, this whole part here, okay? What if we go the other way around? So the book, for example, will often say something like this. Suppose it says x tilde n01. What does that mean? How do we interpret that? Want to take a shot? So how do we read it from here, right? Let's just follow along, right? How would we read it just using that format?
With the
we have another taker. Go ahead.
on the last one, would the mean be 0 and the standard deviation be 1?
Right. So we say that x is a normally distributed random variable. It has a mean of 0 and a standard deviation of 1. Okay. So we're going to be using that notation now and then. It's really handy. Okay. So a really important thing that we're going to emphasize a lot is the fact that probabilities are areas. Okay. And percentiles are areas and tails. So if I'm given any distribution at all, I've drawn this like a normal distribution, but it can be anything at all, okay? The area under that curve has to be 1. That's important. And then we said, okay, we have to give up the idea of talking about the probability of specific values occurring, right? The only thing we can do is we can talk about the probability that the variable has a value in some interval. That's what makes sense. And what that is actually the area under this curve. Okay. So if I want to find this probability, I want to find the probability that the random variables in this interval, I find this interval, I shade in the area under the curve in that interval, and that area is actually the probability. So thinking of probabilities as areas is something that's new to us. It's not something we naturally do, but we're going to be doing a lot. And the probabilities we're going to be most interested in are percentiles. And so percentiles are areas and tails. So if you're given a specific value of a random variable, and I want to know what is the percentile of x, what I'm going to do is shade in that area. This is the left-hand tail of x. And so the percentile of x is going to be the area of the left-hand tail of x. That's how we're going to start thinking about percentiles, okay? So we talked then about how to actually compute probabilities with normal distribution. And we said, okay, what we go to StatCrunch under stat calculator normal. So you're telling StatCrunch, I want to do a calculation with a normal distribution. And this little window popped up after we did that. And so now what you need to do is you need to tell StatCrunch what normal distribution do you want, and how do you do that? Well, the normal distribution is totally determined by the mean and the standard deviation, right? So the next step we did was we entered the mean and the standard deviation. So this tells StatCrunch what normal distribution you want to work with. And then we saw that we could do 4 different things with StatCrunch. Okay, first of all, if we toggle on this standard thing here, we saw that we could input a value here and we could get the percentile. Or we could go backwards. You could enter the percentile here, and you could get the value corresponding to that percentile. Okay. And then if we toggle this little between icon, we could kind of do the same sort of thing, except now we put in 2 values, and we could find the probability between those 2 values, right? And conversely, if I gave the middle percentage, okay, I could find the values that bracketed that middle percent. So we can do a lot right now. And so just to kind of test ourselves, let's do some of these calculations quickly, just to kind of refresh our memory, all right? So we'll go into StatCrunch. And the first question, what price is in the 85th percentile? So notice, if you think about that last slide, what you're doing is you're always going from a data value to a percentile or the other way. Okay, so here I'm going from a percentile to a data value. And so I know that the SOB data, I said that it had a normal distribution with a mean of 29.5K and a standard deviation of 9.5. So for this distribution, I want to know what is the 85th percentile. So let's go ahead back into StatCrunch now. Okay. And so we'll go to Stat Calculator Normal. Okay. And I'm going from a percentile to a data value. So I'm going to put in the probability. So I want the 85th percentile. I'm going to put in 8.5. And is that the right answer? Why not? Right. I didn't specify the right normal distribution, right? So I should have 29.5 and 3.5. Good. Always make sure that you do that. Now let's see what we get. So now we're finding out that it's roughly 33.13. Okay. Notice that this number here, this is this area, okay? And I know that I'm doing this right because I want the percentile. It's the probability that I'm less than. So this is doing the right side, okay? So roughly 33.13 is going to be the 85th percentile. We'll just round it off. Everybody good on that? Okay. So let's see. Let's try another one. What percentile? What is the percentile for the price 35,000? So I'm rounding this off just using thousands. Okay. So let's find the percentile for 35K. So I'm just going to go ahead and type in 35. And there we go. So what are we getting for the answer here? Roughly about what? 94. About 94. Good. Good. Okay. That's good. So our answer is roughly about 94%. All right, great. Let's see. So what percentage of SOBs cost between 23,000 and 39,000? Cost between, what do we say, 23 and 39. So that will be. So, okay, so I go over to here, but I don't have two numbers. How do I do that? Switch to between. Good. Notice you actually could do it if you were really old school. You could do it by computing the probability that you're less than 39 and subtracting it from the probability of less than 23. But that's too much work, right? 23, 39. And it looks like it's about 96%. When you're doing the homework, it's really a good idea to check the picture and make sure that what you think you're doing is what you're doing. It's really easy to make mistakes, okay? So I want the probability that I get a value between 23 and 39, so that looks good. I know it's that area. That's about 96.5%. What do we say, 96.5%. All right, so the last question is, what prices are going to give us the middle 50%? Let me go back to the problems here. Here we go. Okay. So what prices contain the middle 50% of the data? What does the middle 50% of the data mean?
Between the 25th and 75th.
Right. To be the middle 50%, here's what we're looking for. We're looking for the values where 50% of the data is here, and so 25% of the data is here, 25% of the data is here. So we want to find these two values, okay? And so we can do that, right? Just go into StatCrunch, and I'm just going to say 0.5, and there we go. So it's telling us that the middle 50% of the costs or the prices of the socks are between 27,000 roughly and about 31,000. Do we know Q1 from this? Well, if this is the middle 50%, this is 25%, so this must be the first quartile, right? This is the value that's 25% below it. This has to have 25% up here, so this must be Q3, and that difference is the inner quartile range, okay? All right, good. Okay, so this is kind of a review of everything we've normal. There we go. We're just going to take this as a fact right now. If you give me any normal random variable, doesn't matter what the mean, what the standard deviation is, and you compute the z-scores for that normal random variable, the z-scores have a normal distribution. And it's always the same normal distribution. It has a mean of 0 and a standard deviation of 1. And so because it's the same distribution for every random variable, we call this the standard normal distribution. So the standard normal distribution is a special normal distribution. It's the only one that's named. It's a normal distribution that has a mean of 0, a standard deviation of 1. Notice when you go to StatCrunch, that's the default, right? The mean 0, the standard deviation is 1, because we use it a lot, okay? And we know how to write this, okay? So the z-scores from a normal random variable always have this distribution. And we're going to use this a lot. So here's what we'll do. We're going to take a real quick break, and what I'd like you to do is to open up my stat lab, and there are some homework problems in there that are practice. Go back up here. There. So if you go to StatCrunch, let's see, escape from this. I mean, if you go to my stat lab, right? It should be this one right here. Okay. And we're gonna work on that when we come back. Okay. All right. We'll take 5. All right, so why don't we try some of these? So it says an incoming MBA student took placement exams in economics and mathematics. In economics, she scored 84, and in math, 86. The overall results on the economic exam had a mean of 75 and a standard deviation of 9, while the mean math score was 66 with a standard deviation of 12. On which exam did she do better than with the other students? So what sort of problem is this, first of all? What are they asking for here? They're giving us the deviation for each of those tests and the scores. Right, so this is just kind of like the situation where we want to compare two things, apples and oranges, right? We want to compare her score in math or a score in economics, so we're going to look at the z-score. There's different ways of doing this. One way that kind of helps, especially if you're doing it on an exam or a homework or whatever, is to make a little table. In fact, you can even make a table in Excel, okay? I'll just make the table up here. So I might want to put econ here, and of course your values are a little bit different, but the idea is the same, right? So here's her score, here's the mean from the exams, the standard deviation, and the z-score. And you can go ahead and fill this table in with the numbers that you have from your problem. So in my problem, let's see, she had an 84 in econ, 86 in math. Okay. And in econ, the average was 75 and the standard deviation was 9. And in math, it was 66 and a standard deviation of 12. So remember how we compute the z-score. We're going to take the data value, which is the score, subtract it from the mean, and then divide by the standard deviation. So it's telling us how many standard deviations above or below the mean. So if I do this here, let's see, what am I going to get? So the z-score is going to be 84 minus 75 over 9, right? And that's just going to give me 9 over 9 and 1. And here it's going to be 86 minus 66 divided by 12, 20 over 12, 5/3, and that's going to be 1.66, okay? So let's go ahead and answer it for my problem now. I'll let you guys do it for yours. So let's see. For economics, she scored 1 standard deviation. Is it above or below the mean? How do we know that it's above? The z-score is positive. You can actually just tell by looking at the scores, right? But when the z-score is positive, it means that we're above the mean. Good. And they want 2 decimal places, so we're going to do 1.67. And again, that was above. So which one did she do better on? She had a higher score in math, so she must have done better in math, right? She had an 86. So she did better in math. Is that what the question is asking? No. That is not. What is it asking? Which is really a measure of what? Right, we're looking at her relative standing, that's right. So the higher z-score means she has a better relative standing. So here her score stood higher in the distribution of scores than for the econ. Excellent. So she did better on the math exam. Ta-da. So any questions on that one? So z-scores hopefully are pretty straightforward, okay, as far as how to compute them. It says your company's human resource department administers a test of executive aptitude. They report the test grades as z-scores, and you got a z-score of 2.16. What does that mean? I'll pick on somebody new today. So you, yeah. What does that mean if you had a z-score positive 2.16? So what is a z-score? This is really important. A z-score is how many standard deviations you are from the mean. Okay. So this is literally what it is. Okay. So the way I'm going to interpret a z-score of 2.16, right? What am I going to say? That's telling me what? I'll pick on you today.
So that's above the mean.
Can you be a little more specific?
2.16 above.
2.16 what?
Standard deviation.
Standard deviation, exactly. Right, good. Okay. So it's just a number of standard deviations, and the sign tells you if it's above or below. Very good. All right. Now this is a really good problem. So now your company administers an executive aptitude test. They report the test grades as z-scores again, and you got a score of 1.2. They will admit to the executive training program only people who score in the top 1%. Now yours is going to be different, but follow this on mine, okay? Now here's what I'm going to do. I'm going to do something that looks a little unusual, but it's really cool, and it'll make a lot of sense once you see it. I'm going to realize that I could rewrite the empirical rule. Remember when we talked about the empirical rule, we said we never cared about the data values to begin with, right? We only cared how far they were from the mean in units of standard deviation, which meant what? We only cared about their z-score. So I can rewrite the empirical rule like this. And this is how we're going to start to think about it. What I'm going to do is I'm just going to do this. I'm just going to write down the z-score. And now I can start to say some things, right? I can say that when the z-score is between -1 and 1, and I have a mound-shaped distribution, right? The data is kind of mound-shaped. How many values have a z-score between -1 and 1? That's equivalent to asking how much of the population is within 1 standard deviation, right? It's the same thing. So what is that answer? 68%, exactly, right? Nothing new, we know it. We're just putting this in a slightly different form, okay? So there's 68% here. How many do you think have a z-score between -2 and +2? 95%, right? This is the same as asking what percentage of the data values are within 2 standard deviations of the mean. And finally, the 3 standard deviations, it's that 99.7, right? Notice the really cool thing about writing it this way. I don't know anything at all about the distribution. This holds for any distribution at all, right? I just plotted z-scores, and as long as the z-scores have a mound shape, this is gonna hold, okay? All right, so let's go back to the problem. So the problem said I had a z-score of 1.2. Okay, so I was right here. Actually, I scored a lot higher, but it's okay. Okay, so there's a z-score of 1.2. They're looking for people that are in the top first percentile. So am I in the top first percentile? Not even close. But how do we know that? I mean, it's kind of obvious probably, but from looking at it. But how do we know that? How could you really show that?
You have to be like high 2 or near 3 to be in the top 1%.
I agree, but why? Why is that?
Once you reach those standard deviations, well, your z-score puts you in those percentages. Like it tells you where you sit.
Okay, well, I'm going to belabor this example a little bit just to really understand what's going on. Suppose I had a z-score of 2. Suppose I did better and I had a z-score of 2. What percentile would I be in then? Close.
2.5.
2.5%. So it's a 5% divided by 2, right? So if I had a z-score of 2, there's 95% here, right? 5% in the tails, 2.5%. So in this tail, there's an area of 2.5%. Okay? This is the area of this tail. So let me ask you a question. If the area of this tail is 2.5%, do you think the area in this tail is more than 2.5 or less than 2.5? 2.5? More than 2.5? Absolutely. So this is more than the 2.5th percentile. Okay. So I know for a fact I'm not in the first percentile, right? So this area right here is going to be greater than 2.5. So I'm definitely not in the first percentile. And your reasoning is absolutely correct. But we just want to nail it down. What I really want to emphasize here is this notion of areas and tails. Okay, that this upper percentile is the area in the upper tail. Okay, so if this has 2.5% in its upper tail, this area is definitely bigger, right? It has to have more than 2.5% in its upper tail. Again, thinking of probability of the areas, this is kind of a new thing. Someone give me one of their problems, because I know you guys all have different things. So which one that's very different? What do you have, Nathan?
See the z-score is 0.8.
0.8, and so what are you trying to figure out? Top 15 percentile. This is a really good one. Okay. So we'll erase all this and just start over. So here's 0.8, right? So we want to know, is 0.8 in the top 15th percentile? Yes or no? What do you think?
Yes.
Okay. You're shaking your head no and disagreement there. Why do you disagree?
It's less than 1 standard deviation, right? So it's less than 1 standard deviation than 68%.
Yeah, so what are we really trying to do? We're actually trying to find the percentile for 1, right? That's a good place to start. If this is in the 15th percentile, then we can't do anything. So what is the percentile of 1? In other words, if I ask, what is the area in the right-hand tail of 1? What is that? 16%, right? So let me ask you a question. In fact, I'll ask you, what is the question I want to ask now? If there's 16% in this tail, is there more than 16% in this tail? Is this area bigger? Is this area bigger or is this area bigger? Here. Just so there's no confusion. Okay. Which is bigger? Is this area bigger or is this area bigger? Second one, right? So this has to be more than 16%, right? So there's no way that's in the 15th percentile. Okay? So that's how we're going to start thinking about percentiles, with areas and tails. Okay? That's how we're gonna do this sort of comparison. Any questions about that? Okay. What do we say? We said do not. All right, good. Now notice that there was something that we were kind of assuming. Notice I'm using the empirical rule. What do I need to use the empirical rule? Does it work for any distribution? Anything? That's Chebyshev's, right? So what do I need to know in order to use it? Normal, if it's normal, it'll be exact, but I don't have to be, I don't need that strong a condition. I can actually weaken those conditions a little bit. It has to be normal-like, which means what? Symmetric and normal. That's enough, right? And when you think about it, it kind of makes sense. I mean, grades usually have a kind of normal distribution, a kind of mile-shaped distribution. Depends on the class and the test, right? But normally that's true. Okay, good. Okay. Okay, so you know, your mileage will vary, pardon the pun, but you're going to have different mileages than I will, but we'll just kind of follow along here. So fuel economy estimates for automobiles built 1 year predicted a mean of 23.8 and a standard deviation of 7.2 miles per gallon. Assume a normal model can be applied. By the way, what does model mean, normal model? We're going to see that term a lot. Does anybody know what that means or want to take a guess? So model is another word for distribution. So remember when we were talking about the big picture of statistics? The step that we're on right now is called a statistical model. So a model is the way that you represent data, right? So we're modeling data. So when we use the word model, that's synonymous with distribution. So you're going to hear a lot of times the book talk about the standard normal model. What they mean is a standard normal distribution. So this is nothing new. Usually model means the distribution that we're using to model data with, but it's kind of a general term, okay? Okay, so I want you to look at your problems and tell me how you solved yours. When somebody figures it out, just let me know. Did anybody figure this out correctly yet? Got it? I think that. How did you get yours? And so the simplest way, the laziest way to do it, first of all, is to look at the mean, make sure they all have the same mean, and shucks, they do. So you can't roll any of them out, right? But then you look at one standard deviation away. So in my case, one standard deviation away ends up being 31. But when I look at this, there's only one option that has 31. This is the beta values that's one standard deviation away, right? So this is 27.4, this is 38.2, this is 31. So that's the easiest way to tell. All right. So without really doing the work, what interval would contain 68% of the autos? And to be specific, the central 68%. What will we use here? Exactly. This is just the empirical rule, right? So in this case, I know this is the right answer, so I'm going to use this value, 16.6 and 31. Okay. These are one standard deviation away for a normal distribution that's going to have 68% of the values in the center. So check and make sure that it's working on yours, okay? So here they're asking, and let me ask you a question. In everyone's question, is it basically asking what percentage of the automobiles get more than one standard deviation from the mean? Here's this 3, okay, all right. So here the way I'm going to do this, right, is saying what percentage of the autos get more than 31 miles a gallon. I look here, this is one standard deviation away, and we just solved this problem, right? We found that was 16%. If it was 3 standard deviations away, what would the answer be? What's that? So we got to be really careful. So if we were 3 standard deviations away, right, there's 99.7 here, right? And we want to know what percentage have more than 3 standard deviations away. So what would that be? If there's 99.7 here, right, everything has to add up to 100%. Okay, so this is 99.7, so these two tails have to be what? 0.3%, right? Divided by 2, be 0.15%, okay? Just be careful that you enter it in a decimal form, okay? And last but not least, so this is a good problem. So it wants to know what percentage of the autos get between 31 and 38 miles per gallon. And again, I'm not going to bother writing all those numbers out. I'm just going to write the z-scores, okay? So what I want is I want the probability so in this problem, 31 is 1 standard deviation away, okay? And 38.2 is 2 standard deviations away. And so I want this area right here. How can I get that? There's more than one way. What do you think? I'll take a shot.
Just subtract that area from the whole.
Okay, so so let's kind of go a little bit further.
Well, 1 standard deviation is 69.
Okay, so in here is 68%, right?
68%. So if you take that, divide by 2, that'll give you 1 standard. For one side, then go ahead and subtract it. Subtract that number from 95, and then subtract that from the 90, the 67, you should be able to get that 1 standard deviation.
Okay, so let's see. So that kind of makes sense. Let's see. So we want to say that this is 68%, this is 95, right? So the difference between 68 and 95 is these two guys here. Does that make sense? So we say, what, 95 minus 68, so we're going to get, what, 27%? And then what would I have to do just to get this one? Divide it by 2, right? Does anyone have another way of doing it? There's actually more than one way.
You can just take the 67 divided by 2.
I'm sorry?
68 divided by
So if I divide it by 2, I'll get this area here, right?
Yeah.
But I want this area, so how would that help me?
No, I'm saying, you divide it by 2, you get 27 as we got here, divided by 2, and you already got 4.
Okay, but if I wanted to get it another way, rather than using the center, I could use the tails also, right? Yeah.
So say like find the probability is less than 2, the probability that it's less than 1, and subtract the probability that it's less. You do probability that's less than 2 minus the probability that's less than 1, and that'll leave you with that area there.
And I'm going to use your logic, but I'm going to do the flip. I'm going to look greater than, okay? I'm going to look at the tails. Because I know the probability in this tail. What is this? It's 16%, right? What is the probability in the tail of 2? 2.5%, right? So if I subtract off this tail from this tail, I'm going to get this. And that will also give me 13.5. So there's a lot of different ways to do this, okay? There's more than one way to count a skin, right? So to speak. Okay. Oops. Any questions on that though? Hopefully one of those ways makes sense. You can either use the center or you can use the tail. But in this case, the tails are a little bit faster, even though we're used to thinking about the center, right? And finally it says, describe the gas mileage of the best 2.5% of the cars. Well, how many people have 2.5%, the best 2.5%? Okay, so how would we do that?
You just look at like the right side of like the second standard deviation way.
Exactly right. You just find the data value that's 2 standard deviations above the mean. I know there's 2.5% of the tails. Okay. So thinking in terms of z-scores, even though it takes a little while to get used to, once you start to do it, it's very, very natural. That's how we actually think about this. Remember I said in the very beginning, I said statistics is not mathematics. It's actually logic, okay? It's not logic. Some of the things make sense to you and are obvious. Some of the things don't make sense and are obvious. This stuff isn't obvious. But once you see it and you kind of understand the logic, then hopefully it falls together. So let's see, for me, what is that? 38.2. Okay, good deal. All right. So this is one of my favorite ones. And of course, that's always a teacher hint for, I'll put this on an exam, right? That's what they mean when they say that. Let's see, so here we're given a standard normal model. And again, model just means distribution. Okay, I'm just looking at a standard normal distribution. And I want to draw a picture of it first. So what they're asking me to do, actually, is they're asking me to draw a picture of this. So which of these regions represents the z-scores that are bigger than 1.65? Which ones do you think? C. C. Right. Why can't it be that one? I mean, these values are greater than 1.65. Why can't that be right?
That's negative. It's on the wrong side of the mean.
So you're using a fact about standard normal. We're using a fact that the standard normal has a mean of 0, right? So we're actually using this fact that the standard normal looks like this. 0 is at the center. Remember, standard normal means this. Okay? So 1.65 must be up here. And the area greater than 1.65 is there. Good. And now it wants the probability. So these are really easy in StatCrunch, right? And in fact, I'm going to let you guys work on this. I'm going to go around see how you're doing. I want you to work on the rest of this problem. And when you get done, let me know if you get them all correct. The last one particularly is kind of difficult. That's absolutely right.
Good job. I can't see the numbers. Good job. Oh.
No, they actually give me a second.
You should come and see me, I should follow Okay.
My computer died. Which is alarmed because they said it had an hour left an hour.
That's what happened to me last class. Murphy's Law.
Everything's bullshit, so quit.
So when you get them wrong, let me know. We'll see what you did. It's impossible as to have a picture of the So here's something to think about when you're doing this calculation. Is every time you're going from a data value to a percentile or vice versa, right? If you're going from a data value, that's what you're entering on the left-hand side, right? You're getting out the percentile on the right. If you're working with a percentile, you start with that on the right. So, you see that? Did you type 25? Oh, yeah, that's right. That's it. You can see that. Anybody get to the absolute value yet? Yeah, that's one. That's a good problem. That's a problem. I don't like this stuff. What's that? So let me ask you a question. Suppose it talks about the absolute value of z being greater than 2. What does that mean?
It's all the scores that are above 2 and below -2.
Right. Absolute value is a distance from 0, right? So we're talking about this. I'm just making up on something, right? All right. That's what that means. How would we find that? Again, there's a couple different ways of doing that. There's actually 3 different ways of doing that.
How are you finding the percentage? Just put in mean of 0, standard deviation of 1, and then you could input what. Yeah.
I meant from the standard deviation is the z-square.
No. Yeah, it's the outside. So you use to find the inside and just subtract it from 100.
So that's the other thing. Make sure that you enter it as a percentage also. Okay. So for the absolute value, you can compute the probability of the upper tail multiplied by 2, the lower tail multiplied by 2, or you can do the between. That's the easy way, right? And that will also give it to you. Oh, I see. You just want my number. That's cool. Some people try to use calculators, area calculators. Excellent. I'm being careful about that. I knew that. Oh dear, you could. There's actually no closed form solution. There's no closed form solution of these things. So you have to use some sort of tables or calculators or computers. So this probability is actually this interval. So if you want the probability here, it's actually this interval. And there's no, you can prove mathematically that there's actually no formula for getting something like this. So, yeah, unfortunately. And the thing is, it actually looks like an easy integral, because, you know, if this was just z to the first, that would be easy to do. That's actually a known integral. But that z squared screws everything up. So Louisville, like 300 years ago, proved you just can't do it. It's impossible. So, yeah. And that's why we need stack crunch. Okay, so we're kind of getting solutions to period. So go ahead and try to make sure you can get them. We're gonna pick up on Tuesday and kind of finish up the problems, and then we're gonna finish up the standard normal. Okay. All right, looks good. Thanks a lot.